let's just talk about general strategies of how to approach these problems. So one of the things that we have talked about is, Maggie, what's the first thing we should always do when we're given a molecular formula?
Find degrees of unsaturation.
Yep, we always want to do this calculation first because it's going to give us some vital information. So 2 times number of carbons plus 2 plus the number of nitrogens minus the number of halogens minus the number of hydrogens. And in this case, it's 18 all over 2. So I'm going to get 18 plus 2. Yep, so 2 over 2 is 1. All right, so I know I have a degree of unsaturation of 1. So that tells me a couple of things. One, that's going to tell me that I don't have an aromatic benzene ring, right? Also, if I look at my proton NMR, I don't see any peaks between 6 and 8, so that confirms that. Um, but I do have an oxygen. So what should you think when you see multiple oxygens in this type of problem and you have a degree of unsaturation of 1?
You may have a carbonyl. Well, you have a carbonyl, but you don't know if it's an ether or an ester.
Yep. So in this case, what I'm going to assume, and again, this is an assumption, is that when I have oxygens like this, I'm probably going to have a double bonded O somewhere in my molecule, right? I don't know what it's going to be. I could have an ester like this. That would account for both oxygens. Um, Maggie, could I have an alcohol or a carboxylic acid based on the NMR that you see here?
Um, I want to say no.
Morgan, do you agree with her?
I have no idea.
Okay. So, what is something you should have handy, for on your computer that we've talked about before? Your notes, right? So, what is the one type of note that you should make sure you have handy, ready to go on this test? Yes, your peaks and shifts. If you have a hard time reading them, what you can do is just make a sheet that says, something like, you know, alcohol, like 3 to 5, wide peak or something like that, right? Benzene, 6 to 8. You can have little notes like that, whatever you have handy. So if I had a carboxylic acid, I would have a peak around 12. Do you see a peak anywhere near 12? No. So that is going to eliminate the carboxylic acid. That's one good thing that I can say right off the bat, is that I don't have anything above 12. So that's going to eliminate that. How do alcohols, so if I had an alcohol, or just for example, say I had a thiol, or say I had an amine, do those give me splitting patterns, or do I just get a wide peak?
You get a wide peak. Like
Yep.
for alcohols, you get like a huge, like one
Yep.
peak.
For these right here in my NMR, I do not get things like this. I don't get doublets. I don't get triplets. I don't get splitting patterns. When I have something like one of these, it's going to be kind of like a wide singlet. All right. So I will ask you again, do you think I have an alcohol on this one?
No.
Nope, because I don't have a wide singlet anywhere. Right. So usually when you have these, it's going to be between 3 and 5, and they're going to be wide. But I don't see anything like that. Right? All of my peaks split. So that means all of my hydrogens are going to be on carbons. Does that make sense? When your
Yes.
hydrogens are on carbons, that's when you get these weird splitting patterns, things like doublets, triplets, stuff like that. You can still get singlets, but when they're on oxygens, when they're on sulfurs, when they're on nitrogens, whatever, that's when you get these wide peaks. They don't split. You'll never be able to tell. You can only tell by the integration. Okay. The next thing you want to do is that we see that nice splitting pattern on top, but the first thing we should look at is going to be our integration. All right. So, for those of you that haven't seen any of these, how do you tell what the integration pattern is if you have these type of red lines? Do you know, Morgan?
Like how many H's are on there?
Yep, now it tells us how many H's, but we have these little red lines. Do you know what those red lines tell us?
No.
They are the relative ratios of protons. So if I compared the height of this red line, and I'll make it a little clearer. So this is the height of this red line here, right? Like this. And then this is the height of this red line. What is that ratio? Does that look like to you guys? Does it look like it's
Like the one's like 2 times bigger than the little one?
okay? Yeah, like it's about, like it's about 2 to 1, right? So that means that this integration ratio is going to be a 2. This is going to be a 1. This one and this one appear to be the same height, correct? So this is also going to be 2. This one also appears to be the same height. So that's going to be 2. And this one's a little bit higher, but that's also going to be 2 because that looks to be about the same height, right? And then this one here, what does this one look like?
I said 3 for that one.
Yep, it looks like it's a 3, right? Because it's not quite as big as both of these together, which would be 4, but it's not quite as small. So this is probably a 3. And now I'm going to kind of erase these lines to help us out here. What does this big one look like? And this big one is about here to here. Any idea what that looks like?
A 6.
It looks like 6, right? So this looks like this is 6. So it looks like 2, 2, 1, 2, 3, 6. So let's add those up. 6 plus 3 is 9. Plus 2 is going to be 13. Plus 1 is 14. Plus 2 is 18. How many hydrogens do we have in our molecule?
18.
18. So we know that our ratios have added up correctly. So that's the way you can check that. Does that make sense?
Yeah.
What would be, so like when you're going into these problems, what's like the step process that you would recommend like starting with to figure it out?
Oh, that's what we're doing right now.
So like you would do the degrees of unsaturation and then count the
So degrees of unsaturation first.
Yeah.
And figure out if you have what you have, right? And remember, if you have a degree of unsaturation of 4, what should you automatically think? If you have a degree of unsaturation of 4 or more, what should be your first thought?
benzene.
Benzene ring, right? And so you just figure out, do I have a double bond, whatever, so just figure out that first. Next thing is we want to figure out our relative integrations if they are not given to us, which is what we just did, right?
Yeah.
Okay,
Why
so what?
So on the red lines, why do they have that like break in them?
Like this right here?
Yeah.
Because this height is occurring to this one, and then this second height is occurring to this peak, is related to that one.
Okay. Gotcha.
Does that make sense?
Yeah.
Okay, so I am just going to scroll up, and we are going to use the more clear line. And so this was, I believe, 2, 2, nope. Sorry. Just click all of this off. So if I remember correctly, Maggie, it was 2, 2, 1, 2, 2, 3, 6.
Yeah.
Okay, so now we know what the degrees of unsaturation are. We know that what our relative integrations are. So here's what I would think of next, Morgan. Is now I'm going to look for things that I can recognize. I look for specific splitting patterns that tell me, aha, I know that when I see this splitting pattern, I know that this functional group is here, all right? So things like alcohols. Do I see a white peak if I have an oxygen, right? Do I see something in the aromatic region, 6 to 8, like a benzene ring, like if my degree of unsaturation was 4 or greater, things like that. But do you guys see any type of functional group based on what you see here? Can you clearly see something?
We're like, it's like around 4.
Mm-hmm.
That would be like the oxygen, like where the oxygen is.
Yep, I'm probably going to have a carbon there, right, attached to that. But there's something even easier to see. There's a bigger, more obvious functional group.
The isopropyl.
There is an isopropyl group, right? So when I see a doublet with an integration of 6, and then I see a huge multiplet with an integration of 1, this is indicative of an isopropyl group? Because if I call these two hydrogen groups A, they are both next to this one proton, right? So since they both have one neighbor, they're both going to be a doublet. And so 3 and 3 is going to give me 6. So that's why this is going to be A, right? Now, how many peaks are in that? It's kind of hard to count, but how many peaks do you see in there?
2.
Sorry, in wrong one. My bad. How many peaks do you see here? Because now we're looking at this one. We're going to call this hydrogen B.
There's 7.
Count again. Look at the very edges. I know this isn't great if you're blind. If you notice at the extreme edges, there are actually 2 very small peaks there.
Oh,
There's 9.
interesting.
Can you see that, or is that very hard to distinguish?
I can't see it. I'm blind.
Okay, that's fine. This is a tricky problem, but always take a zoom in look as best you can, right? Like make your screen as big as possible and see if you. So I'm going to do this real quick. I'm going to zoom in, and I'll show you what I mean. So this is going to make stuff look a little weird, but can you see right here now at the very edges that there are just the smallest little nubs? This is what in the industry, this is what we call a dick move. Just because they're really hard to see, right? But that's fine. So I'm gonna zoom back out. But this is good now. At least now you can recognize that it's there. All right. So if there's 9 peaks, how many neighbors does my B signal have?
8.
Right. So I have 3 here. I have 3 here. How many more must there be? Next.
2 more. Wait, 6.
Yep.
3 more.
2 more.
No, 2 more.
Right. So it's going to be next to what type of group?
The isopropyl.
Nope. The isopropyl group. So if this one has 8 neighbors, there's a CH3, a CH3. What else has to be attached to that carbon? CH, what? CH1, CH2, oxygen. CH2, right? Because that's the only way you're going to get 8 neighbors is if you have that CH2. Does that make sense?
Yeah.
Right? Because this just tells us how many neighbors we have. All right, so now I'm on a CH2. Okay, so let's think about this. Right now, this CH2, and I'm going to call you, we will call you C. All right. How many neighbors does that CH2 have right now?
Only 1. Wait, 2.
This one?
Wouldn't that be 1?
It has 1 neighbor right now, right? Because here, right, this is its only neighbor right now, right? So right now, I only have 1 neighbor, okay? So how many could I have on the other side? What's the most amount of hydrogens I could have on the other side right now? This, in theory, it could be connected to a CH2, right? On the other side. Or it could be connected to an oxygen, or it could be connected to a CH. Do you know which one of those is possible? Or you can't tell right now? We don't know.
Would it? Oh.
Well, it's because there's a lot of possibilities, right? We don't know what the splitting pattern is going to be. We just know it has 1 neighbor right now, right? Do any of these peaks that we have not eliminated, could any of those peaks be your, can we eliminate any of those other peaks possibly? So by that, I mean, we've already labeled A and B. Can we eliminate any of these ones from potential candidates as being connected?
The one very downfield.
You're saying that we can eliminate this one?
Yeah.
Why do you say that?
Oh,
I'm not saying you're right or wrong. I'm just curious as to your reasoning here.
Because wait, I changed my. I think it's the one right next to the A peak.
Yep, we cannot have this one here. Why
Oh.
can't we have that one here? That I'm putting the huge underline under.
Because that has to be at the end.
Yep, remember, if we have a proton signal that has an integration of 3, 6, or 9, it represents some type of CH3, right? So either a CH3 by itself, or an isopropyl group, or a tert-butyl group, right? So when we get to a tert-butyl, an isopropyl, or a CH3, that is the end of a chain. So because it has 3 protons, it can't be in the middle. It has to be at the end, right? Does that make sense?
Yes.
Morgan, you look a little confused.
Yeah, I'm just kind of confused.
So
But-
if I have a CH3, right? If I have a signal that has 3 protons like this one here, right? How many more things can that carbon be connected to?
One.
One more thing, right? So it can only go this direction. It can only be at the end of a chain. It can't be in the middle.
Right. Oh, okay.
Does that make sense?
So the peaks don't go in order.
No, they
Let's
go
do
they go by relative electronegativity, how close they are to electronegative things.
Okay.
All right, so right now I am going to throw out the idea that you can figure out what goes. You can figure out what peak this is right now, but I'm going to say you guys probably just don't have the confidence in yourself to make that leap. So what we're going to do is we've started on one side of the chain, right? Here, we started on this side of the chain, and I think that that side looks good. What should be your next step if you're trying to make a chain? What should we do now?
Do we have to find where the oxygen goes?
We can try and find where the oxygen goes, but there's something a little bit better that we can do. If I know what one side of my chain looks like, I can possibly
Try and figure out what the other
chain
end
looks like.
like.
Yep, so which one of these peaks, based on their integration, has to be the other end?
This
The one next to A.
Yep, because it's got 3. So I'm going to call you, and I'm just labeling willy-nilly, I'm going to call you, we will call you, how many peaks do we have? 1, 2, 3, 4, 5, 6, 7. So
Has to be G.
we're going to call you G. We will call you G. I'm going to, let's go with green. Green's a color. So we're going to call you G. All right, so we're going to say that this is CH3. So based on its splitting pattern, right, how many neighbors does it have?
2.
2.
2, because it's a triplet, so we subtract 1. So what does it have to be connected to then? If it has 2 neighbors,
CH2.
CH2, right? It has to be connected to a CH2. This carbon can only have how many attachments, Morgan? How many
One more.
bonds? One more bond. So if it can only connect to 1 carbon and it has to be connected to 2 protons, it has to be a CH2.
Okay.
Right? Does that make sense?
Yeah.
Okay, so looking at my remaining signals, do any of those jump out at you as it could be, or can we eliminate any of them?
Could it be the one next to B to the right?
So
Yeah.
like this one here or this one?
The pen. Yeah.
Okay, why can't it be this one?
Because it only has
Is
one
that
neighbor.
one neighbor?
Yeah, it only has 1 neighbor. And right now, and actually I'm going to change the color here to make this life a little bit easier for
One
us.
of the other ones has 4 and 5 neighbors.
Yep, because that's 100% correct. And great job on that thinking. Is that now this CH2, right? It already has 3 neighbors here. So it cannot be that one because this only has 1 neighbor. It cannot be this one because it only has 2 neighbors, right? So that just leaves this one and this one. So this one is going to have 4 neighbors and this one is going to have 5 neighbors, correct?
Yes.
So
Yeah.
if you were a betting person, which one would you go for?
5.
Yep, it's going to be this one because if now it is connected to another CH2 because it's got an integration of 2, right? That carbon can only have 1 more bond. How many neighbors does this have?
5.
5. And so that's why it has to be this one. So now we are going to call this F. So you're going to be peak F, like that. Does that make sense for how we made that deductive leap of reasoning? Okay. So now I'm going to erase this and clear some of our stuff off here. So that we're... Okay, so this is F. So now we only have 3 more peaks to worry about, right? So we need to label this peak right here. So how many neighbors does it have right now?
2.
It has 2, right? So it could be this one, or it could be this one, right? We don't know yet. If you were a betting person, which one would you go for?
Four,
Or-
maybe?
Go ahead.
It's probably going to be this one.
1.5, yeah.
So I'm going to call this one, I'm going to change the color back to orange. This is E. This is probably going to be E as well. Okay, so now how many neighbors does that one have? How many neighbors does this have?
Oh, 4.
4. So there's 2 to the left. So to the right, it has to be
CH2.
CH2, right? So now this should be starting to come together. And now, how many neighbors does this one have that I'm going to call peak D?
2.
It has 2. So can there be anything to the right with protons? Because it already has 2 neighbors.
No.
Yeah.
So what do we have left? We have a carbon.
With the
We have a carbon with a we have a carbon double bonded to oxygen because we know we need to have that in there, right? Nothing else is telling us that there's a double bond or a ring or anything else. Since we have 2 oxygens, we're going to work under the assumption that we have this right now. We have an ester, but we don't know how that goes in. So going back now, we are going to say then that this is, what's the only peak that we have not labeled successfully?
the
A, B,
W.
C, D, E, or F.
Oh,
So we have, I'm going to show you what I'm talking about here. So we have peak A, which we said is here. We have peak B, which we said was here. We have peak C, we have not labeled. We have peak G, which we said was here. We have peak F, which we said was here. We have peak E, which we said was here. So this is our only peak that we have not labeled. So this has to be C. Does that make sense?
yeah.
All right. So now,
You go through and maybe you pick the wrong peak for like your F. Will it come back at the end and then you can like fix it, or will you just end up doing it wrong?
yeah, like if you went through and you said, oh, it looks like this isn't working, then go back and try and fix it.
Okay.
All right. All right. So now I'm going to, can I clear off these notes?
Yeah.
Okay. I'm going to clear off just to give us a little bit more room here. So right now, I'm going to draw what we have so far. We have 1, 2, 3, 4. We don't know what's here. Then we have, oh, it's bad drawing. Okay, so we don't know what's going to go in the middle. So based on what we have, we need to put this in between, this ester. So this signal right here, we said is C. This signal right here, right, we said was D. Okay, so when we think about our ester, and I'm going to put a little bit to the left. Which side is going to connect to D? Which side is going to connect to C? How can you tell?
I think the side where it's just like the oxygen connected to just like a single bond oxygen, I think it's gonna connect to C.
Do you guys agree or disagree with that? And why do you say that?
Okay, so C has, if I'm looking at this right, C,
Don't even, okay, there's something even easier here. And I think you're maybe making this a little more complicated. Which one of my peaks is further downfield?
the C is.
Okay, so which one, my CH peaks at C or my carbon peaks at D, which one is going to be attached to the more electronegative atom?
C.
C. So what's more electronegative, a carbon or an oxygen?
Oxygen.
So which one should be connected to C?
The oxygen.
The oxygen.
Yep, because it is further downfield. Remember, the further downfield it is, the more electronegative. So what my molecule looks like in all of its grandeur is going to be this. That's what my structure looks like. Does this make sense for how we put that together?
Mm-hmm.
Okay, now this is probably the part where you guys are saying, hey, Terry, this is all well and good, but you're not going to be with me tomorrow. You're not going to be able to hold my hand when we're doing this. So what is the one piece of advice that I've always given you guys when you're taking a test like this? And you have to do something like this that is a multi-step thing. What is the one thing I've always told you when it comes to these types of problems?
Be consistent.
Well, be consistent. Yes, that's always true. But there's something even more related to points.
Count your carbons.
That's being consistent. Those are the same thing.
Oh.
No, imagine you guys are the point grubbing little monsters that you really are. And think about what's the one thing I've always told you, though, when it comes to these tests. Put as much information down as you can. Show that you calculated degrees of unsaturation. Show that you saw that we have most likely an isopropyl group, right? Know that this is a CH3. If you can't make that final connection, you cannot connect everything. But if you get all of the fragments out, at least demonstrating that you are aware of what is present and what's not is going to help you. Does that make sense? So label everything you can, okay? It's going to help you out in the long run.
I think it's multiple choice. I think she said.
Is it all multiple choice? You don't have to do like a drawing for these?
I think that's what she said.
Okay. Well, still though, you should be able to think through these and think about what's present in there. So let's try this one. So see what you guys can get. I'm gonna just kind of scroll down here a little bit more. So see what you can get from here. And your formula is up there in the top left. So what's the first thing you should always do when you get to this type of problem?
Degrees of unsaturation.
Calculate degrees of unsaturation first, because that is going to help you. And I get a degrees of unsaturation of?
You're at 5.
Yep.
Does
So
that mean
since I have a degree of unsaturation of 4 or more, what should be your first thought?
A benzene ring.
Where do I look on my NMR to confirm or deny that?
Like 6.5 to 8.5.
Yep, I look between 6 and 8. And I see peaks between 6 and 8. So do I have a benzene ring in there?
Yeah.
Yes, I do. All right.
does 5 mean 2 rings?
No, 5. So remember, each degree of unsaturation means that you have a double bond or a ring. So benzene has how many degrees of unsaturation?
4.
4. There are 3 double bonds in there, right? 3 pi bonds, and then there's 1 ring. So in this case, I could have another ring of some sort. It wouldn't be aromatic, but I could have a 6-membered ring. I could have a 5-membered ring, right? I don't know. I have an oxygen. I might have a carbonyl, right? I don't know. So that's why I have to play around with it. If you get the IR, it makes life a little bit easier, right?
Yeah.
Okay. So try to draw everything you can here. See what you can get, and I'll give you guys a couple of minutes. I'm going to go. I made some coffee because I was very tired. I meant to go to the store earlier and buy stuff to make jambalaya, but I just didn't have the energy to walk the half mile to the store.
Jambalaya is so good.
Mhm. I live on the coast now, so seafood's like, available and cheap.
Mm.
So needed to buy some shrimp and a couple of vegetables. That's all right. I'll be right back.